Welcome to This Explainer. Today we're exploring something we all rely on pretty much every single day, but we rarely stop to think about how it actually works mechanically. Yep, we're talking about the air conditioner. Instead of just treating it like some magical cold air box in the window or the backyard, we're going to break down the really elegant refrigeration cycle, the chemistry of the refrigerants, and the whole mechanical loop that makes it all happen. It's actually fascinating, so let's jump right in.
Okay, let's dive into this and immediately clear up a super common misconception. Does your AC actually make cold air? Well, the answer is absolutely no. There is no machine inside your house generating chilliness out of thin air. Instead, what they do is simply remove heat and humidity from the air that's already inside your home. They basically grab the unwanted heat and they transfer it outside. So you aren't really pumping cold air in, you're literally just pumping the heat out.
So to understand exactly how that heat extraction happens, we really have to look at the foundational physics of cooling. And it all comes down to a pretty remarkable physical law called phase conversion. Simply put, when a liquid converts into a gas, like when it evaporates, it absorbs heat from its surroundings. Air conditioners exploit this natural feature by forcing these special chemical compounds, which we call refrigerants, to evaporate and condense over and over again in a closed, continuous loop. These refrigerants are basically the lifeblood of the whole system because they have these unique properties that allow them to change states at relatively low temperatures.
Now, an absolutely crucial point here is understanding exactly what kind of heat we're dealing with. Because as your AC runs, it's actually tackling two totally distinct types of heat energy. First up, there's sensible heat. This is the heat you can physically feel, the heat that actually changes the temperature of the air in the room. By absorbing sensible heat, the AC is what lowers the reading on your thermostat. But then there's also latent heat. This is the energy that's trapped in the water vapor, or the humidity floating around in your air. As the AC cools the air, moisture naturally condenses out of it. By removing this latent heat, the air becomes much drier. This is exactly why your AC doesn't just make you cold. It makes the air feel crisp and comfortable. It makes this totally invisible thermodynamic process highly tangible for all of us.
Now, what's really interesting about this slide is how it maps out the layout of a typical split-system air conditioner, the central air most of us have in our homes. We can clearly divide the mechanics into two distinct zones. Inside the house, you've got the cold side, featuring the evaporator coils, and their job is purely to absorb heat. Outside the house, you've got the hot side, featuring the condenser coils, whose sole job is to release that absorbed heat into the outdoor environment. It's a really brilliant two-part system working in perfect harmony. So let's look a little closer at the indoor side. Right inside your home sits the evaporator coil, which is usually made of highly conductive copper or aluminum. I really want you to think of this coil as a giant heat sponge. As the warm air from your house gets drawn through the return ducts and blown across these freezing cold coils, the liquid refrigerant inside them goes right to work. It undergoes that phase conversion we just talked about, evaporating into a gas. And as it evaporates, it absolutely soaks up the heat from your indoor air. That newly chilled air is then circulated right back into your living room. But now we've got a bit of a problem. The refrigerant is full of heat and it's turned into a gas. So what happens next?
Well, that heated refrigerant gas leaves your house through a copper tube and travels out to the outdoor unit, going straight into the compressor. Now, the compressor is essentially a large, incredibly powerful electric pump. Its entire job is to take that warm, low-pressure gas and literally squeeze it. By packing all those gas molecules super tightly together, the compressor drastically raises both the pressure and the temperature of the refrigerant. You see, we actually have to make it hotter than the outside summer air so that it can successfully release its heat.
Okay, so now, superheated and highly pressurized, that gas flows into the outdoor condenser coils. Out here, a really large fan pulls the ambient outside air and blows it right across those coils. Because the pressurized gas inside is hotter than the summer air outside, the heat transfers right out of the refrigerant and into the outdoor air. As it rejects all that heat, the refrigerant cools down and condenses, turning back from a gas into a liquid. Boom! The heat from your living room has officially been banished to the backyard.
But hold on, we aren't done yet. The refrigerant is a liquid again, sure, but it's still under really high pressure, and it's not quite cold enough to cool your house yet. It travels back inside and hits a really critical component, the expansion valve. This little valve forces the liquid through a tiny opening, which causes an abrupt and massive drop in pressure. This sudden drop causes what engineers call adiabatic flash evaporation. It instantly and drastically cools the liquid refrigerant down to a freezing temperature, perfectly prepping it to head right back into the evaporator coil to absorb more heat.
And this brilliantly illustrates the entire elegant journey. It is essentially an endless relay race of thermodynamics. Step 1. The compressor pressurizes the gas. Step 2. The condenser releases the heat outdoors. Step 3. The expansion valve drops the pressure to flash cool the liquid. And Step 4. The evaporator absorbs the heat from your home, starting the whole cycle all over again. It just keeps looping and looping until your thermostat says, yep, the room is perfectly comfortable.
Now, since we're looking at the mechanics, let's inject a little myth-busting energy here, because there are a couple of very common misconceptions about how this loop works. First myth: AC units pull fresh air from the outside to cool your home. Busted! No way! As we just learned, central air systems actually just recirculate your indoor air, passing it over those cold coils again and again. The outdoor unit just rejects heat. It definitely doesn't pump outdoor air inside. Second myth: air conditioners need their refrigerant refilled every year. Busted again, because the refrigeration cycle is a totally closed loop. The refrigerant is literally never used up. You should only ever need a recharge if your system has a physical leak.
Now, believe it or not, this core technology isn't actually a new concept. The foundational design goes all the way back to July 17, 1902, when a young engineer named Willis Carrier invented the very first modern air conditioning system to control humidity in a printing plant. But what is truly amazing is how incredibly scalable his fundamental design actually is. The exact same closed-loop principles that are cooling your bedroom right now are at work in massive industrial setups, like the Carrier Aqua Edge centrifugal chiller we're looking at here, which is used to cool gigantic skyscrapers, huge hospitals, and massive industrial plants today.
Let's move to and see how this builds when we look at the chemicals flowing inside these systems, because they've had to evolve dramatically. Back in the 1980s, we used CFCs, but those were phased out globally by the Montreal Protocol because their chlorine content was actively destroying the Earth's ozone layer. That led us to HCFCs like R22 in the 90s, and then to HFCs like R410A in the 2000s, which are entirely chlorine-free. But because HFCs still have a pretty high global warming potential if they happen to leak, the future of the industry is rapidly shifting toward HFOs and even supercritical carbon dioxide, known as R744, which have a tiny fraction of the environmental impact. But it's not just the chemicals that have changed. The actual mechanical efficiency of the system has also taken a massive modern leap forward, largely thanks to something called inverter technology. Historically, an AC compressor motor was either entirely on or entirely off. There was no in-between. It ran at 100% capacity until the room was cold, and then it abruptly shut down. Inverter technology completely changes the game by using magnets and electric current to seamlessly and efficiently control the motor's speed. It basically eliminates all that wasted stop and start operation.
To vividly picture this, the HVAC engineers at Daikin use a fantastic analogy comparing it to a runner. So a non-inverter AC is like a runner who sprints as fast as humanly possible, stops dead to rest, and then sprints at full speed again. It's totally exhausting and it consumes a massive amount of energy. An inverter AC, on the other hand, is like a marathon runner who finds a smooth, steady, continuous pace. By just slightly adjusting their speed up or down without ever coming to a full stop, they maintain momentum perfectly and without wasting a single ounce of energy. This is a real game changer, and it's exactly how modern ACs save you so much money on your power bill.
Which brings us to the future of indoor comfort. We've mastered the physics of phase conversion, we've built incredibly efficient inverter-driven compressors, and we've totally unlocked the process of pulling heat right out of thin air to keep our homes beautifully comfortable. But it leaves us with an ongoing challenge to balance our personal comfort with the health of the planet. As the world gets hotter and the demand for air conditioning naturally skyrockets globally, can our coolants continue to become greener? It's a fascinating engineering puzzle, and it's one that the brightest minds in the industry are racing to solve right now. Thank you so much for joining me on this explainer, and keep staying curious.